Well, hello everybody. This is the new tutorial. It took a while because I've been preparing interesting stuff to get more deeply into coding inside Rhino, and I will move forward to other things in the next series of tutorials. I had some requests from people trying to, I don't know, asking me to teach more, professional. I don't know if that's the word, but workflows. So I'm preparing stuff with Revit, Dynamo, Fusion 360, which I think is one of my favorite platforms. For now, I'm sticking to Rhino and Grasshopper because I know it's the one that most of the people use. But even though I posted in this channel some tutorials about basic stuff that I will add more things about introductory or more basic stuff in the future. I want to dedicate this couple of videos about getting really into coding inside not Rhino but Grasshopper to see why it's useful also to implement some coding once in a while. I did a little bit of that with the runway tutorials. But now we're going to do something that probably, I don't know, using another plugins like Anemone or Hoopsnake, the ones that allows you to do, for example, loops and stuff, is not enough. And basically want to try to keep things simple, especially if we are trying to share the things that we produce so other people can understand it. What we are going to do today is we are going to implement reaction diffusion. And if we go to Wikipedia, a reaction diffusion system basically is are mathematical models which correspond to physical phenomena. Basically, these are naturally applied to chemistry, as you can see here. Basically, it's the simulation of different components reacting to each other and how they diffuse to create patterns that you can find, I don't know, coral reefs, or I don't know, the patterns of a weird fish, or the skin of a tiger or zebra. If you go to Wikipedia, you can find a pretty good explanation about how this system works, and especially the equations that are the ones that we're going to use here. But if you see here, for example, these are typical reaction diffusion systems with different parameters of substances reacting to each other, and you can generate all sorts of interesting stuff. There are some interesting equations to simulate this. For example, the BC, the Belousov-Zhabotinsky. We have the Gray-Scott, that is actually the one that we are going to use. It basically takes two components and we simulate according to the parameters over time how they react. You'll see why. Well, we have seen remarkable examples about that, about this implementation. So for example, if you don't know nervous system, a really nice design and fabrication, digital design and fabrication studio, they took this inspiration from animals to create this type of interesting model. So for example, this reaction lamp, this is simulated using probably the same Gray-Scott reaction diffusion system. If you listen to my printer, I'm printing some masks now for the quarantine, so I'm sorry about the noise. So we will try to simulate this. There are two things that we need to consider. Python, and in general, actually, most of the simulations are done in more suitable environments, programming environments, to do this. For example, the most ideal will be using open frameworks, for example, that works. That basically it's super fast because it's based on C++, or I don't know, to do it in coding languages that allow you to do parallel computing. So because these are super heavy in terms of computational power, requirements, so probably this will be a little bit slow, but I mean, it's okay. We will simulate, because in order to simulate like more accurately like advanced patterns like this, you need more iterations, and that increase the time like exponentially. We will try to keep or balance our parameters to simulate this reaction in 3D. That's also like another difference. Like most of the implementations that you will see, for example, in processing or other things, are 2D based, like pixel calculations. We will try to trick or cheat this to basically keep it or use it in 3D. So the first thing that we're going to do, of course, is open Rhino, open Grasshopper, and we will start coding our simulation. For that, remember, if you're using Rhino 6, you have the Python. If you go to Math, Script, and Python Script, you will have this by default installed. If you're using Rhino 5, you need to go to Food for Rhino and download the Python script component. So your definition can include this. So first things first, we want to create some initial parameters for our simulation. So in order to do that, we are going to just a second. We need to specify our initial parameters. So if you remember, the scripting component has like the possibility of specifying inputs here on the left side of the node, and here what we are going to need are basically 1, 2, 3, 4, 5. We're going to use 5 inputs. We are going to name first. We are going to work. We are going to simulate this reaction diffusion system on a surface. So the first thing that we need to specify is an input for the surface. We change the name by right-clicking on the name, and here we're going to say this is an item access because we're going to access only one data, not a list. And we are going to say that the type of this data is the surface. So we will help the script to realize this. The second one will be which, basically, because we will be playing with two types of components. Basically, we will react with a substance or a concentration, let's say, of A, right? Substance A and substance B. So we want to basically choose which one are we going to basically get which result, because we're gonna get either the concentration of A or B. So we are going to say that this is an item access. We're going to say that this is a string. We will use a string for doing that. Concentration. Let's name it like that. It's okay. We will need a. Basically, what we're going to do. We are going to divide the surface in a grid. So we need to specify the resolution of this grid. So we will say like height. Yeah, that's fine. We're going to say that this is item access. This is an integer. And this is width. Actually, not width. Width. This is also an integer. We will not use caps for this. And also, we want to control also like the height of the 3D, like some sort of like thickness of this. I will explain what this is. We're gonna say that this is I don't know, like C factor, for example. Let's call it like that. And this will be a float number. So with that we are actually okay. We will produce now a surface component that we will get from Rhino. We will instantiate from Rhino. Here, let's create just a panel. We will say A, B, right click, multiline data. So basically we have two options. Here we will do a list item, and we will say 2. Sorry, it should be so we can pick between 0 and 1. So we pick 0, A or B, right? So we will connect this here. For this, we will start with, I don't know, like 80. We will do just like equal amount of divisions for, I don't know what I call it. This is let's call this resolution, because this will be like the more resolution you have, the better is basically like the quality of the final geometry that you will get. For now, I think with 80, it's a lot, but you will see then when we activate the profiler, the thing that affect the most the simulation or the quality of what we're getting actually are the iterations. So for this, we need one more input, is or steps. Actually, we will call it steps. This will be an integer, and we will set this to, for now, to 200. 200 is like an intermediate number for getting, like, I don't know, in my computer it takes like about 8 seconds to calculate the values. I will show you in another video, like a bonus video, how to, for example, improve a little bit this by calculating outside, for example, with a Google Colab. Basically generating files that you load afterwards. You do the pre-calculation. That actually helps a lot, and we will do that in a Google Colab. Why? Because we have the possibility of getting rid of all geometry generation, and basically it's just like pure data that we're generating. Like we will use Pickle to generate like binary files that you can generate and load super fast inside Rhino using the Pickle component that basically encodes the data into like binary files, and then you can decode them and use them and not calculate everything in real time. That's a little bit faster. And also we will try to use NumPy, but that's a little bit complicated, so this is why I will add it as a bonus tutorial for this, because even though now we can use NumPy, that NumPy brings like many benefits to this type of like hardcore calculations, especially for the Euler integration that we are going to do here. We will do like integration of differential equations. But the problem is that, yeah, the current implementation, Grasshopper Remote, even though it's great, because with I will show you what it is, still it's kind of slow. It's a little bit slow. So this is why the next series we will finish with Python, doing that, implementing NumPy, and then we will move to C# to do based on also like an old code. This is a code that I produced, by the way, like almost 9 years ago for a workshop in Chile for the school where I am a professor, and we never used it. It was part of the initial ideas, but I was like really into this because I was introduced this by a colleague. So I think it's like pretty relevant now that you see implementations like the one that I show you in nervous systems, and many people also used it. I don't know, like Neri Oxman had this like glove that's supposed to cure like carpal tunnel or something like that. So you see implementations that are using it, and why not like teach you how to do it? And okay, so let's go back to this. So we will say that this is, I don't know, like 0.1. And okay, I think we're okay with the parameters that we need. So let's get into the proper coding. First thing first, when you open this, you will see the Python editor, and you will see, yeah, like here, for example, what is like what are how things work. Basically, our output right now is A. Basically, this is like a placeholder, and after we produce something by code, we can say that A is equal to the thing that we produce, and then we can use that with the regular Grasshopper nodes. The first thing that it comes by default is the RhinoScript syntax as RS. So basically, that means that I can call the all the methods or functions that Rhino API has. So for example, how would you add a point? And when you open the parentheses, it says that, oh, you should provide a point. So you can say point add, and here no, sorry, we will do it. I don't need to do it now, but basically it's saying that if you do just RhinoScript syntax, you will have to do, instead of doing RS, you will have to write that. So basically you can give it an alias RS. So you can say RS that add curve, for example, or add arc, or add a circle, for example. So you can specify a plane, a radius. Basically down here you have all the parameters that the constructor of this class is asking you. That it was a point vector. That's anyway. We will work with this. So let's start coding. We need to do some other imports first. So we will actually do hashtag. This will be a commented line. This will not execute any type of code. So we will say that these are our imports. We will import math. Math will allow us to basically do like typical mathematical operations like add or things like that. We will also import random as R&D. This will allow us to, from the Python language, generate random numbers, because one of the things that we need to do is to start with random values to actually start our reaction. So yeah, we need to generate random numbers. So that is why we need to basically import this functionality. What else? Just in case, if we want to access Grasshopper classes, I don't know if we will. We can, for example, CLR, that is the Common Language Runtime. So this will allow us to add references. So CLR that add reference. So here we will add Grasshopper, and maybe we'll use data trees. I don't want to get like too creative, because we already have a lot to cover. So we will say like from Grasshopper kernel, and we can say data import everything. So with this we are importing like everything that we need in order to generate like data trees, for example. from Grasshopper import data tree. And just in case, I will put this just in case we need it. Sometimes I like to get a little bit creative in order to do this tutorials, but probably I don't want to extend this too much. So first things first, we need to we need to create a matrix. And yeah, probably because this is old code, probably there are better ways to do this or more efficient. Again, with NumPy you can do it like in a very easy way or using list comprehensions. I want to keep these things as simple as possible, but also be like very pedagogical about it. So list comprehension is something that's at some point would, I don't know, if you're not used to them, they can blow your mind and basically like give you a headache because it's hard to read. So even though that people say that Python is a really nice language, it has some things that are really hard to read. So this is why, I don't know, in my opinion, I like it. I love Python. I hate JavaScript because it's like total opposite to be like really direct language. But I love C# because basically it asks you to be like very explicit about the instruction that you're doing. If you use list comprehensions, it's a little bit tricky, so it doesn't matter. So first we will create a matrix, and for this matrix actually we need another parameter that we will include soon. We'll call it like init matrix, and for this we will need a seed. Basically it's just like a number that will generate like different random patterns. So we'll call it random seed. No, actually for that we will use, okay, that's fine. We will define some global parameters. Global first A0, B0, and yeah, actually here we will use the random. Actually we don't need this. We can do it. We can say that random, or do we need it? Yeah, let's do it like that. Okay. So basically these are global parameters for our two components. We will do like random rnd, that's seed. Sorry about my typos, it's just that I really don't like my MacBook Pro keyboard, it's really bad. So here we will generate two empty lists and we will populate those lists with random numbers. For I in range, basically we will do a loop. So basically it will say like start for every I number that will be like an incremental number, integer like 0, 1, 2. Basically this is what is called a loop. We will do height. Basically it's the same. We can choose height or width because those are the same numbers. We'll start with height. This A, for example, and this will create an empty list. Empty list, just like Grasshopper list. If you're familiar with Grasshopper, this basically is a container with a list of data that we will use. This B equals to also like another empty list. So here we will say for J in range, but basically this is a double loop, and I will explain the structure immediately. Width, and I have a typo here. Remember that each, oh no, it's okay. 2 points. This is the syntax. Every time that you declare like a loop, you write the loop, you have to do the colon. symbol, and here basically we will add this a that append R&D that random how can we do this? Because this is really like almost like, yeah, like 9-year-old code. I don't know why. I'm checking my notes. I did this, but let's trust that this is okay. R&D that random times 2. This will generate like a bunch of random numbers. Okay. I will try the version without this stuff, ridiculous stuff. But let's see what happens with this. Oops. Sorry, it's just again the confusion between Mac and Windows, because I'm working with a Mac to do this. This is this B. Yeah, this is okay. So now we want to say that A0 that append, and we will append the values of this A, and B0 that append this B. And we will say here, just for debugging purposes, and again, I don't know if I mentioned this because but the component, the Python component inside Grasshopper, it's based on Python. It's one of the flavors of Python, and it's based on Python 2, which is no longer supported by. It's no longer supported now. Everything that you do, you must do it hopefully in Python 3 if you want to get support from like libraries that you want to add or things like that. So this is why if you want to use this code in a Python 3 implementation, some things will change in terms of syntax. So for example, now to print something, I just say like print A0, for example. But if you're in Python 3, you want to do
mostly I want to help.
That, I don't know why Siri thought that I was calling her. Sorry about that. Print A0. Oh, it sounds like hey Siri. There she goes again. Okay, so print A0. You have to put parentheses if you want to print it in Rhino. I'm sorry, in Python 3. So let's test if this is working. It gave us a error, of course, says that unexpected token. Yes, of course. When you define a function, in this case, we are creating the matrix, we need to also add this. So let's say line 34, and in that we have an indentation problem here. Line 34, yes. Yes, okay. So this is also that it's basic for Python, but you might want to know what it is. The way that you know that you maintain the structure of the code, this is actually pretty nice in Python, that it's according to this, the tabulation of your lines. So if you're creating a for loop, sometimes you want to use, I mean in other languages like, I don't know, like Java or C# or C++, when you declare a loop, you use curly brackets to basically create the loops. Like everything that is inside those curly brackets is the things that will be repeated according to the iterations that you're specifying. Here in Python, it's basically that is defined by the tabulation, the indentation, sorry. So you may want to check that everything is in line. So global name A0 is not defined. Oh yeah, it's giving me let's do this inside print A0. Okay, good. We have something. Basically, this is not doing anything because we are not calling this definition. We don't have any errors. So let's do something. Let's do print init matrix. Let's say 0.1. This, we're passing this value basically to try to do this. Global name A0 is not defined. Why? 940. It's giving some problems. And anyway, let's move on. We don't need to do anything with this. Actually, one thing that we can say is A equal to A0 maybe. Let's add a panel here. It's actually good to add a panel to get error messages. And here, yeah, this is giving me a null. That's fine. We don't want to worry. We don't want to worry too much about that. So let's continue. Basically, this will just populate, as I was saying, our matrix with random values. So actually, for some reason, yeah, it's not. Oh, I know why. Well, this is the cause. Anyway, it doesn't matter. Just want to see if this is doing anything. Init matrix. Oh yeah, okay. That's the thing. It's giving me an error about like global numbers. We need this global specification here because we will use it in later. So as you can see, this is actually, we can say this A equals to init matrix. It's not executing it when we do that. Okay, I will comment this for now. What I can do, I can say that return this A, for example. Yeah, A equals, okay, this will work. For now, we will modify this later. So we are generating those random numbers here. What we're saying is that this function that I'm calling here init matrix, and that's the random seed number that I'm assigning to generate like the randomness. I'm saying that, let me get rid of that print statement. I'm commenting this because that's giving me the error. I'm just saying that generate the random numbers and return a list of random numbers to the A output. So if I say OK, you see that this is generating those numbers here. Actually, this is generating just one part of that. So temp values. So we can say, we'll leave this A0, we can say temp vals dot append this A. And actually we will return this. This return statement is saying that once you do everything, like when I call this function, you will return these values. You will give me those values that I'm calculating. If I don't do anything, it will just execute things. It doesn't necessarily have to like return something. So okay, we see that now it's not giving me individual values. Here we're saying that if I say that the number of iterations are 100, this is giving me 100 lists with 100 random numbers. So that is actually quite cool, and it's fast. See, this is giving me like, and the problem, I mean, probably this is why we will need, if we I don't know, I'm not sure about it, but right now it's giving me a specific data type that is IronPython runtime list, and that is something that I show you in the runway tutorial. It's a type that Grasshopper doesn't understand, but this is being returned by this component. So again, and to finish this first tutorial part, I will show you if you ever need like generating like random numbers. You can create data trees, but if you're lazy or you don't have the time, you can do something as simple as this. You just create a C# component, because C# understands those data types. This is a really nice trick that I wish I knew it before. You can say that A, basically the output of this C# node, is equal to X. And it's giving me some sort of error. Oh, of course, yes, you need to add the semicolon here. And if you copy and paste this guy, you will get exactly what we are looking for. A list, Grasshopper list with, in this case, we have 50 values, so it will generate 50 lists with 50 values. So we have the data tree viewer. You see, it's generating this data structure. 50 lists with a total of 50 values each. So that's pretty nice. This is the first part of the tutorial. This will be divided in 3 tutorials, plus the bonus one, where I will show you how to use the Python remote to actually use, for example, SciPy or NumPy. So thank you very much, and we will continue from here for the next tutorial where we will implement the actual equations. Thank you very much.